So, Yaniv Balmas is a software engineer, and he started tinkering with a Commodore C64 when he was 8 years old. And he was kind of a teenage hacker of games as well. And now he's in the security field, and he got interested in the fax machine. Together with his friend Eyal Itkin, who is also a security guy and malware researcher, and together they're going to tell us about the fax machines and what the fax, why still using people those machines. And it's going to be really interesting, I think. And the title is also Hacking Your Network Like It's 1980 Again. I'm really excited. Please give a warm round of applause to those two guys.
Thank you guys. Hi, CCC. You probably know this sound, right? And now get to know us. So my name is Yaniv Balmas. I'm a security researcher. I work at Checkpoint Research. And with me here today is Eyal Itkin, also a security researcher, also it's Checkpoint Research. And let's begin with talking a bit about the history of fax. So I guess that not many of you know that fax started. It was first invented in 1846 by a scientist called Alexander Bain. Fun fact, this happened 20 years before the invention of the light bulb. And then it had some more advances to it. This is the actual first thing that looked like a fax machine, like a standard fax machine. And again, this thing was invented 20 years before the invention of the telephone. So humanity was sending faxes before we had light or talked over the phone. And then there was some more advancements like radio fax. And another important point in time is 1966, where a small unknown company called Xerox came out with the first commercial fax machine. This is the advertisement for it. And in 1980, a strange organization called ITU defined the current standards for fax. Namely, it's T30, T4, T6, and those standards are still the same standards that we use today, basically, with just minor changes to them. So this was all in the past, but what's happening today? I mean, today we have far better ways to send electronic documents from one to the other, right? You know, let's compare fax to just, I don't know, off the top of my head, just, you know, one method like, let's say, email. And just to, you know, remind you, we are comparing this to this, okay? So let's look at some of the features here. In terms of quality, yeah, okay. In terms of accessibility, I'm pretty sure that all of you here have 24/7 access to emails. Not so sure you're carrying around your fax machines with you. In terms of reliability, well, you know, when you send a fax, you don't really know if it got received or not. Yes, there is this strange confirmation page, but it doesn't really mean anything. I mean, if there's no paper in the receiving fax, you still get it. If the dog ate it, you still get it. So there's absolutely no reliability in fax. And regarding authenticity, well, we can argue about emails, if it's authenticated or not. It could be forged, of course. But we do have public key cryptography and stuff like that that will help us when talking about emails. What we don't have nothing when it comes to fax. Absolutely no authenticity. So if we're looking at this table, one might think to himself, okay, so who the hell still uses fax today? It's 2018. I mean, it deserves a place in the museum of great technologies, and that's it. So nobody is using fax today, right? Yeah, wrong. Everybody are using fax today. And you see, fax is used like to send these very critical maritime maps to ships at open seas. 90% of the Japanese population uses fax, according to Wikipedia at least. And if you Google any kind of combos like contact us and fax or stuff like that, you will come up with something like 300 million results, 300 million published fax numbers in Google. And that's not counting the unpublished numbers, right? That's a huge amount of numbers. But it's not all about numbers. I mean, it's not how many fax machines are out there, but it's also who is using fax. You see, if you're a small corporate, a medium corporate, a huge corporate, you have fax. Not necessarily anybody is sending fax to this number, but there is a fax machine sitting there waiting for a fax to be received. If you're a bank, you simply love faxes. This is Bank of China, the biggest bank of the world, in the world, and that's the fax number of it. And I think most importantly, if you're a government organization, you simply wake up in the morning and you want to have more fax. So this is Donald Trump's fax number. If anybody wants to send him a fax, go ahead. That's it. It's not a secret. It's from Google. So we should send him something, by the way. Yeah. And the thing is that, you know, those banks and government institutions, they don't only support fax, allow you to send fax. The funny thing is that actually most of the time it's mandatory to send fax. There is no other way. You can either postal mail it or fax it. They didn't hear about anything else. So we looked at this state of affairs, strange state of affairs, and said to ourselves, you know, this looks strange. I mean, it can be true. Humanity came so far, and we are still using these old technologies. So what the fax? And like, we decided to try and do something about it. And we started a very long research to try and find some security vulnerabilities in fax. And before we do that, let me just, you need to explain how fax looks like today. You see, today fax doesn't look like it looked 20 or 30 years ago. Then it was just standalone fax machines, right? Today, fax is mostly old technology embedded within newer technologies. So, I mean, we have fax to email services or email to fax services. We have, like, as I said before, radio fax and fax over satellite and stuff like that. And I think most commonly, we have these machines. All-in-one printers, like you buy them, they scan, they print, and they fax. It actually comes with a phone cable out of the box, so you can connect. I guess most people connect it. And I also think that this is the most common faxing solution today. So we decided to take a look at these machines, these fax machines. And if you look at these boxes, from a security point of view, you can imagine them to be just black boxes, right? And those black boxes has interfaces. So in one side of the box, we have interfaces like Wi-Fi, Bluetooth, Ethernet, stuff like that. These interfaces connect the printer to the internal network, the external network. Basically, it connects it to the world, right? And on the other side of this box, there's this little interface here that connects this black box to somewhere to the 1970s, I would say. So yeah, that's pretty funny. And you know, if you remember that at the end of the day, these printers are basically nothing but computers. I mean, they have CPUs, they have memories, they have operating systems. They are computers, not standard ones, but they are computers. And we were thinking to ourselves, imagine this scenario, right? There's an attacker sitting somewhere in the world. All he has is access to a phone line and his target's fax number. What will happen if this attacker, this guy, would be able to send a malicious fax? And with this malicious fax, he will be able to exploit the printer. Then he's has complete control over the printer, right? If he does that, he could then maybe pivot through any one of those other interfaces, let's say the Ethernet, and jump from this printer to the rest of the network, the internal network, effectively creating like a bridge between the external world and the internal network through the phone line. That's 1980s again. So we thought that this is a really cool tech scenario, and we decided to accept this challenge and go for it and try and actually show this thing happening in reality. We were really excited about this. But then after we slept a bit and drank a bit and sat down and talked about it, we kind of found out that there's like a lot of challenges, really hard challenges in front of us, and we're not really sure how to deal with them. Let me name just a few of them. So one of the challenges is how do we obtain the firmware, the code that this printer runs. It's not like you have it everywhere. And after we get it, how do we analyze this firmware? After we analyze it, we need to understand what operating system are those printers running, and then we need to understand how to debug a printer. I never debugged a printer before, and I need to understand how to debug a printer. And after we do all that, we need to understand how does fax even work. We only know the beeping sounds, like most of us, I think. And after we did all that, we can start talking about where can we find vulnerabilities inside this big, big, big ecosystem. And today we'll try to take you through these challenges one by one and explain how to do it until we'll be able to actually do the thing that the scenario that we just showed you. So let's start with the first challenge. How do we obtain the firmware for the printer? So meet our nice printer. It's an HP printer, an HP OfficeJet printer. We chose this model for, first of all, we chose HP because it has like, I think 40% of the market share, so it's not that we dislike HP, we really like them, but unfortunately for them, they are just the biggest target out there. And this specific model, well, we have a lot of reasons why we chose this printer, but basically, it's the cheapest one. Yes. So we bought it. We didn't have a lot of budget. We bought it and we abused it for a lot of time. And our goal was to break the break fax, right? But before we do that, we had to break the printer, and I mean literally break the printer. So yeah, that was the fun part of the project. We broke it, and inside the printer we find this thing. The main PCB, the brains behind the printer, and it looks like this. Let's map the critical components of it. So we have here a flash ROM, a suspension, some model, and then we have some more memory here. This might look like not a lot because the PCB has two sides to it, of course. And on the other side of it, we have the more interesting components like USB, Wi-Fi, electricity, SRAM, battery. Probably for the memory, but who knows. And now we have two very interesting components here. One of them is the main CPU. It's a Marvel CPU, and it's proprietary manufactured for HP. So we can't, tell anything about. There's no available specs, nothing. We can just find bits of information here and there. And then we have the fax modem. It's located here, and it's a CSP 1040. And what we need to understand now is how does these two components operate and what is the relationship between them. If we do that, we're one step further. So that's what we try to do. And as I said, the first challenge at least is to get the firmware of this thing. And when we're looking a bit closer into this PCB, we find these two very interesting interfaces. One of them is a serial debug, the other is JTAG. So if you're familiar with them, so you know that they give you like debugging capabilities or at least memory read, memory write, exactly what we need to get the firmware. So we're smiling to ourselves saying, this is going to be really easy. But unfortunately, it's not, because the JTAG, of course, is disabled completely. We can't do anything with it. And the serial port, well, we managed to connect to it, and we get this terminal that for almost every instruction we type gives us this error. I don't understand. Well, we don't understand either. But it looks like this terminal is not going to get us very far. So we drop this path and try and look for other ways to get the firmware. And obviously, one of the most common ways is to try and grab the firmware upgrade. And after looking a bit in the internet, we find this Joule, this FTP site by HP that contains every firmware version for every HP product ever produced in the history of HP and the internet and a lot of other stuff. And it actually took us like about, I think, 2 weeks to find our firmware within this mess of firmwares. But once we did, we had a firmware upgrade file. Yes, thank you. It's still alive, so you can go there and look for some. There's a lot of interesting stuff in there. And now we got ourselves a file. And this file is a firmware upgrade file. It's not an executable file. It's just a binary. And now we kind of need to understand, how do you even upgrade a printer firmware? I mean, I never did it before. Anybody did it? Anybody upgraded his firmware lately? Good. Good for you. Good for you. Anyway, the answer to this question is surprisingly funny, I would say. Yeah, you just print it. Yeah, that's because, you see, a printer receives a firmware upgrade just the same way as it receives a normal print job. That's that thing, it's actually pretty nice, and it's defined in a HP protocol. It's called like PCL XL Feature Reference Protocol Class 2.1 supplement. That if you are still sane after reading this like 300 pages of insanity, you understand that this thing defines something called a PJL, a print job language. If you ever scanned the printer through the network, you see this port, I think 9100, something like that, open. That's the port that you send print jobs to, and that's the same port that you send the firmware upgrade to. And that's nice. So when we look at the file, it actually confirms this because it actually begins with the words PJL, print job language. So that's nice. So now we know it's a print job language, but unfortunately this document doesn't document anything about the firmware upgrade protocol or anything because it's like kind of HP proprietary. So unfortunately we had to like do it ourselves and analyze this thing. Now I'm not going to take you through the entire process of unwrapping this firmware because frankly it's quite boring, but I'll just tell you that it's composed of several layers of compression. One of them is called null decoder, the other is called TIFF decoder, and another one called delta row decoder. And the thing is that these things do something like, if the previous line was all blanks, then if this line is also all blanks, just write one instead of the line. So that gives you some kind of compression. And it makes really a lot of sense when you're talking about print jobs, because, print paper has a lot of spaces in it. But when you're talking about binary file, it makes absolutely no sense to do it this way. But still, it just works this way. So after we understand this, that we were able to decode everything, decompress everything, and we're talking to ourselves and laughing that, when you're a hammer, everything looks like a nail, and when you're a printer, everything looks like a print job. That was nice. And now after we did that, we have a big file that hopefully now it's our firmware. So how do we analyze it? So looking at this thing, right at the beginning of the file, there's something that really looks like a table. And doesn't really only look like a table, it is a table. We define it, it looks like this. And what this table defines is like a loading address, section name, and location in binary. So what that means that our big file is actually split into several sections. And this table just defines those sections. So now we are able to split this big file into several smaller chunks and inspect each chunk. And the most important chunk, the one that looks most promising, looks like it contains our firmware. So we took a closer look into that, and that's what we saw. It actually looks like our firmware. That's because, you see, that's like one of the strings that we see in it. Yeah, we all saw that before, right? It's arrow I don't understand, but it's not completely arrow I don't understand, right? There's some missing bytes in here, and we actually, those missing bytes are pretty consistent throughout the entire chunk. So although we know that we are looking at the code, we can't actually see the code until we have those missing bytes filled. We need to understand why aren't they there and what were they replaced with. So let's try to analyze this thing together quickly now. But first, let's start to understand what is this thing. We had a lot of things in mind. Everyone seemed crazy, but I think the least craziest option was that this is yet another form of compression, a really bad one, again, because when we try to compress this thing with zlib, for example, we get like 80% better compression than it currently is. So, and we know that the printer has zlib because we see zlib strings in there, so why not use zlib? I don't know, but still we are left with the challenge. So this is one snippet of the code that you just saw. Let's try to decompress this. So first of all, you need to understand this thing is composed of two types of characters. One are ASCII characters, stuff that you can read, and some other are stuff that you can't read, non-ASCII characters. And those non-ASCII characters are actually those missing bytes that we have. So we need to understand what they are, so let's take a closer look at them. And if you stare at this thing long enough, you'll start seeing some kind of pattern. And I'll save you the trouble and just show you that it's composed of like these one single bytes and then those double bytes in there. And if the distance between the single bytes looks suspiciously patternish, like 8 bytes, 9 bytes, 9 bytes, 8 bytes, over and over again. So what does this mean? Where is the pattern here? If you look at this from a different angle, maybe the pattern will look a bit clearer. You see the F7 and F7, they look the same. The FF and FF, they look the same. Something here looks really patternish. And in order to understand this pattern, you need to sharpen your binary view a bit. And if you understand that FF is just 8 1 bits, and if you do this consistently for all of these chunks, then you'll start seeing the pattern. You see, the pattern is that the 0 bit always falls within this 2-byte hole. And what this means, it's consistent throughout the file. What this means is that the first byte is just a bitmap describing the following 8 bytes after it. That's what it means. And that's perfect, because now we understand what is this single byte, but we still don't understand what are those double bytes, and they were replaced with something, but with what? So if you know anything about compression, you know that there's not a lot of options here, really. It could be either a forward or backward pointer, it could be a dictionary of some sort, or it could be a sliding window. Now, we can pretty easily confirm that it's not a forward backward pointer, just because we try to follow the references in the file. We see nothing that should be there. Same goes for dictionary. We can't find anything that's consistent enough to be a dictionary, so it leaves us only with the option of sliding window. And once we're equipped with this information, we go to our favorite place, to Google, and try to find some similar implementations to this. And luckily for us, in some very dark corner of the internet, we find this wiki page. It defines something called a soft disk library format, I won't ask if anybody knows what soft disk is, because probably somebody knows here. It's CCC after all. But inside this thing, it defines some kind of compression algorithm that looks very similar to ours. It looks actually really, really like ours. Actually, it's exactly our compression algorithm. So yeah, that's nice. And I think that the funny thing here is that this compression algorithm was used in the past, somewhere, and only there. Can you guess where? Yeah, somebody who didn't see who didn't see this presentation before. Yeah, it was used in Commander Keen, and Softdisk is the company who produced Commander Keen. So the compression algorithm from Commander Keen made its way somehow into the HP, the entire HP line of products. How? I don't know. You can check if there was anybody who was fired from Softdisk and hired in HP. Probably that would be my guess, but we'll never know. Now we understand exactly what is this thing and how does this compression work. We have the missing data that we need, and this data means that those 2 bytes are actually composed of window location and data length. And that's all we need. And let me show you, like, really quickly how this compression works. So we have an input text, output text, and sliding window. We want to compress this string over here, and let's try and do it. So first byte is the bitmap, I remind you, so we leave it empty for now. And then second byte, we start with A. So we place it both in the output text and in the sliding window, and then we go to B, same thing, C, same thing, D again, and now we get to A. But A is already present in the sliding window, so we don't need to write it in the output text. You know, we can just write, just do nothing, and then go to B, same thing, it's just the following character in the sliding window. And then when we get to E, we just write 0002. That means go to the sliding window at position 0 and take the first 2 bytes. That's what it means. And then we continue to E, F, G. After we did that, we put our bitmap here, and now we know the bitmap value, and that's all there is to it. That's the compression algorithm. It's pretty easy looking at it this way, right? Looking at it at reverse is a bit more difficult. But yes, now we can do that, and now we completely open everything, and yes, we have our firmware. We can read everything. It's actual code. And now we need to understand what does this code mean. And basically, first of all, we need to understand what architecture is this, what is the operating system, and so on and so on. So it took us quite some time to do that, but let me give you a brief explanation. First of all, the operating system is called ThreadX. It's a real-time operating system. The CPU, the processor is ARM9, big Indian. And then it has like several components to it, like stuff that's related to system, some common libraries, and tasks. Tasks are the equivalent of processes in normal operating systems. So in the system stuff, we have like bootloaders and some networking functionality and some other stuff. In common libraries, we have a lot of common libraries. And tasks, once we are able to isolate them, we can understand exactly the tasks. And once we do that, we now know that all we need to do is like to focus on these tasks because they are the tasks relevant to fax protocols. We can leave everything else aside. It will make our work much more easy. And we want to start doing that. But just a second, before we do that, looking at this, we see something that looks not really, I don't know, it doesn't make sense a lot. And this thing is SpiderMonkey. The printer, every HP printer contains a SpiderMonkey library. And I don't know if you know what SpiderMonkey is, but basically it's the JavaScript implementation by Mozilla. It's used in Firefox, for example. And we were thinking to ourselves, why does a printer need to render JavaScript? It makes no sense. I mean, yeah, it has a web server, but it's not a web client. We couldn't think of any situation in which a printer needs to render JavaScript. It looked really strange to us. So we decided to try and see where this printer is actually using JavaScript. So we went back a bit and checked, and we found that JavaScript is used in a feature called PAC, Proxy Auto Configuration. It's apparently something, no, it's pretty common. It's a common thing. It's a good protocol. And it defines a proxy when you're doing a DHCP or something like that. And the thing is that the top layer functionality of this entire PAC functionality was written by HP. And when we were looking at that, we see all this functionality and we see this strange thing here. The printer, once it does this PAC functionality, it tries to connect to this domain, fakeurl1234.com. Just connect to it and do nothing with it. Some sort of sanity test, I guess. I don't really know why. But the interesting thing here is that, do you know who owns the domain fakeurl1234.com? No, it's not HP. Checkpoint is kind of, yeah, I own it. Yeah, it just wasn't registered. So we registered it for $5, and now every HP printer is connecting to my domain. If anybody wants to buy the domain, I have a very good price for you, more than $5. And now I'll hand it over to Eyal to continue.
Okay, thank you, Yaniv. After we finished messing around with SpiderMonkey, it's time to focus back on fax, or T30. T30, in its full name, it's ITU T recommendation T30. It's the standard that defines the fax protocol. Actually, it's a very, very long PDF, more than 300 pages, that defines all of the faces and messages we need in order to send and receive a fax document. It was first designed very long ago, in 1985, and was last updated more than a decade ago. So from our perspective, that's a very good idea, because we want to find vulnerabilities in an old and complicated protocol. We're most probably going to find some. After we read through the standard, we started to dynamically look at it, open it in IDA, and look up on the T30 task. And you can see that the state machine is quite huge, as you can see here in IDA. And actually, that's a small state machine, because most of the code blocks you can see over here contains additional state machines inside them, meaning that this is going to be a very, very huge and complicated state machine to reverse. And if that wasn't enough, it turns out that HP really likes to use function pointers and global variables in their code, meaning that statically reverse engineering this huge task is going to be very complicated. Although I personally prefer to statically reverse engineer, this time we had to choose a different tactic. We'll need to dynamically reverse engineer this thing, and for this we'll need to have a debugger. And as Yaniv mentioned earlier, nobody knows how can we debug a printer. We already tried built-in JTAG and serial port, and that failed. We then searched for built-in GDB stub we could use, but I couldn't find any such stub. At this point, it's very important to remember that even if we could control the execution flow, no one can put a debugger without controlling the execution flow, and we can't do anything. That's a black box. I can send papers, and that's it. And even if I could control the execution flow and load my debugger, the printer uses a hardware watchdog. And this is an external hardware mechanism that monitors the main CPU. And whenever the main CPU enters an endless loop or halts, the watchdog reboots the entire firmware, the entire printer. And this means that since essentially a breakpoint halts the program, whenever we'll hit a breakpoint, the watchdog will kill us. So we'll need to find a way around this thing. And the easiest way we could find out is to split this enormous task into chunks. If we could find any code execution vulnerability, we could try to execute code over the printer and load our own debugger. And at this stage, we had luck, and we believe that luck is an important part in every research project. Sanrio, on the 19th of July, Sanrio published a vulnerability called Devil's Ivy. Devil's Ivy is a remote code execution in GSOAP. And many embedded devices, and our printer included, tend to implement a web server for management and configuration. And in our case, this web server uses GSOAP, and it even uses a vulnerable version of GSOAP. So we now have a vulnerability, and we'll need to exploit it. For those of you who are not familiar with Devil's Ivy, here is the code, and here is the vulnerability itself. Devil's Ivy is an signed integer underflow vulnerability, meaning that we'll need to send enough data for the variable to go from negative back to positive. And that means we need to send roughly 2 gigabytes of data to the printer. So HP really prides itself on the printing speed of the printers, but not on the network speed. After many optimization rounds, we managed to reduce the exploit time to roughly 7 minutes. So you start the exploit, you wait, and after 7 minutes, you have your exploit. And here, our stroke of good luck ended because we had the side effect in our exploit, and after 2 to 10 minutes, the printer will crash. And this means we'll need to wait an additional 7 minutes. We'll have 2 minutes to debug it, and then it will crash again. So we waited a lot of 7 minutes in our research. If you recall, we wanted a debugger so we could dynamically reverse engineer the firmware. We wanted to read memory and write memory, and now we have a debugging vulnerability so we could load a debugger. We'll need to execute this debugger, so we'll need execute permissions and to load it. And the most important thing is that we need to execute our debugger without crashing the firmware, because we want a debugger to run and a firmware to debug, and we want them to blend inside the virtual address space of the printer, living happily together. We couldn't find any debugger that achieved these goals, so I did what my brother usually tells me not to do. We actually wrote our own debugger. So this is Scout. Scout is an instruction-based debugger. It supports Intel CPUs and ARM CPUs because we have an ARM printer. As a prototype, we had a Linux kernel driver, and this time we're going to use it in embedded mode. In embedded mode, we compile it to be fully position independent because we essentially throw it somewhere inside the firmware and we expect it to execute. We pre-equip it with useful addresses like memcopy, socket, bind, listen, we find using IDA. And whenever it tries to call these functions, it goes to its own GOT, finds the address, and jumps to it. So after we compile it, we use it in our exploit, we jump into this blob, and it starts up a TCP server we can now connect to send instructions to read memory, to write memory, and whatever we want. You can find Scout in our GitHub with the examples for Linux kernel driver and embedded mode, and we're actually using it for some CTFs now, so it's highly recommended. Now that we reached this point in our talk, we haven't yet described to you how a fax actually works. So with Scout, we dynamically reverse engineered the firmware, and now we can actually describe to you how a fax actually works. In order to send a fax, we need a sending machine. We need to send it to some modem. The packets from the modem will be processed in the CPU, and afterwards the data is going to be processed and probably printed. Let's see how it starts. We start with network interaction, probing, enraging, echo-analyzer, echo-canceling, more training, and you actually need to be quite familiar with these steps because they sound like this. With these beeps, we actually created an HDLC tunnel. Through this tunnel, we're going to send our T30 messages to the CPU. In T30, you have phase A, which we send the caller ID, which is a string. In phase B, you negotiate the capabilities, so I send my capabilities and receive the printer's capabilities. Phase C is the important step because here we actually send our fax data, line after line, page after page. And in phase D, we finish. I send an ACK, I receive an ACK, and that's it. Let us now see how a normal black and white fax document is going to be sent through the protocol. So we have our document. It's going to be sent over the HDLC tunnel using T30 messages over phase C, and the received document is actually the body of a T file compressed in G3 or G4 compressions. From our perspective, that's partial good news because there are many vulnerabilities when parsing TIFF headers, and we only control the data of the file. The headers themselves are going to be constructed by the printer itself using messages from phase A and phase B. So we partially control a TIFF file, and after it's done and ready, the file is going to be printed. Like every good protocol, and here comes very interesting, T30 supports many extensions. Can you guess what interesting extensions there are in the protocol? So there's a security extension, but no one uses it. So the other extension is color extension. Actually, you can send colorful faxes, and the British use it in hospitals for some reason. Let us see how a colorful fax works. We send a document through the HDLC tunnel over phase C, and the received document is actually a JPEG file. This time we control the header and the data of the file, and we can do whatever we want with it and send it for printing. Now that we know how a fax actually works, where should we look for vulnerabilities in it? Well, we have complicated state machines with 10 strings. There are several file layers, but the most convenient layer is the applicative one, and most importantly, JPEG, because we control the entire file. If we look on a JPEG file, it mainly consists of markers. We have a startup marker, application marker with length and data, more markers with length and data, and so on and so on. If we zoom in on one such marker, we can see that in this marker we have a compression table, a 4x4 compression matrix for the exact document we send. We have a header, length field, 4x4 matrix, and the data itself. If you zoom in a bit deeper, we can see that here we get the matrix. We sum up all of the values. This matrix should be rather sparse with zeros, ones, and twos. The accumulated value is going to be our length field, in this case 6 bytes. And 6 bytes are going to be copied from the data to a local small stack buffer, like this. So if you can see the vulnerability, at this point we were like, what a fax, because that doesn't make sense. We control the entire header. If we put huge values in our matrix, like so, we'll have a 4 kilobyte length field copied into a stack buffer 256 bytes, effectively having a stack-based buffer overflow in our printer. It's a trivial stack buffer overflow. We have no byte constraints. We can use whatever we want, null bytes, non-ASCII bytes, whatever we want. And 4 kilobyte of user control data, that's more than enough to exploit. At this point, we had to bypass several operating system security mitigations. Nah, not exactly. It's an RTOS, fixed status spaces, no canaries. It's the 80s. It's really simple. We've got the CVEs from HP, 9.8, critical. You should really patch your printers now. And here you can see the response we received from HP after we worked with them to patch these vulnerabilities, which is a good time for our demo.
Unfortunately, we couldn't bring a live demo, so we just filmed something for you. So this is our attacker machine. What we need to do is run this script. It's connected to a modem that we bought in like $10 from Amazon. And we're sending our malicious fax to this printer. And yeah, incoming call from who? Wait, just a second.
Faxes are slow.
Yeah, they are. So from an evil attacker, of course, you can forge this easily. And now the printer is receiving the fax and processing it, and now it's obviously a colorful fax, and now we have full control over the printer, so it's ours. But that's not enough, because we want to show that we can propagate to another computer, so our malicious fax contained eternal blue in it. So once any computer is connected to the network, the fax now will recognize it, and we try to exploit it, and here you go. Yeah. We made it after all. It was a long way. Some conclusions we have to tell you. First, PSTN seems to still be a valid attack surface in 2018. Fax can be used as a gateway to internal networks, and old and outdated protocols probably not so good for you, so try not to use them if you can. What can you do to defend yourself against this catastrophe? A lot of things. First of all, you can patch your printers, as Eyal said. This link will, just tell you if your printer is vulnerable. By the way, every HP inkjet or OfficeJet printer is vulnerable to this thing. That's the biggest line of printers from HP. Over, I think, 200 or 300 models are vulnerable to this thing. So really, go and update. Another thing I can tell you is, if you don't need fax, don't use it. And also, if you do need to use fax, after all, try and make sure your printers are kind of segregated from the rest of the network. So, even if somebody takes over the printers, it will just be confined to the printers and won't be able to take over your entire network. So, guys, these are really good suggestions, all of them. But really, the best suggestion I have to give you today is, please, stop using fax. Thank you. And just 1 second before we finish, this was a long way, a long journey, and through this journey we had some very good friends that helped us a lot along the way, physically, mentally, technically, so we must mention them. These are the guys here. Some of them are in the crowd, so they deserve some claps. And one special guy that helped us is Yanai Livne, and he also deserves this. And that's it, basically, guys. So if you want to follow more of our work, you can find us here. Follow us. Thank you very much.
Thank you very much. We have 5 minutes for Q&A, so please line up at the microphones. If you want to leave now, please do it to your right side. So this side from the stage is the left side, but for you it's the right side. So please line up at the microphones. I think I can see microphone 4 already, so we'll start with microphone 4, please.
First, thank you for this talk. It's scary to see that these things work today. You talked about email to fax or fax to email services. Now I wonder, is it possible that there are vulnerabilities in those as well? I know Fritzbox routers allow fax to email. Could you attack those possibly?
So basically, those services use T30 as well. We didn't look at them, frankly. We had so much work to do with the printer that we didn't look at any other printers or any other services. But I can't say for sure, but if you're looking for vulnerabilities, I would recommend to go look there as well.
Great. Microphone number 5, please.
What can you disclose about the data that's sitting your URL? What can you disclose about the machines that are knocking on your URL? The fake URL 1234.
There are a lot of HP printers out there. That's all I can disclose. Sorry.
So we have one question from the Signal Angel, please.
Did you try to activate JTAG via printing a modified firmware?
We tried to use the JTAG. We think it's disabled from the factory lines. It was too much work, so we decided to use Devil's Ivy. It's a good vulnerability. Once we have Devil's Ivy and we can use Scout, Scout is more than enough for debugging. Essentially, after we used the JPEG vulnerability and we loaded up Scout, Scout survived for weeks on the printer without any crash. So that's more than enough.
Great, we go with microphone number 2, please.
Yes, so thank you for the nice talk, and I think you're completely right. We can have many problems with legacy protocols. The only thing I do not really get was the part how you then can automatically successfully attack your laptop on the network. My point would be my laptop is as secured as I'm going to the internet cafe or something else, so you would not be able with your HP printer to start the calculator on my Linux or even not on my Windows. Is that right?
Your laptop might be secure, I'm sure it is, but many others are not. We try to show this using the Eternal Blue exploit. As you know, WannaCry, stuff like that, you know, this thing created a lot of, and there were patches out there, and still it was. So we're not here to attack anyone. We're just saying that theoretically, if somebody wants to get into the network and he has a vulnerability that you're maybe not patched to or secured, fax would be a bad idea to have.
But it was nothing which was part of the printer. That was
Sorry, unfortunately we don't have more time for Q&A, so thank you again very much.
Thank you.
It's really nice